My name is Netanel Lindner. I'm an assistant professor at the Technion. And I'd like to thank the organizers of this conference and congratulate them for the new center. And today, we'll use this item. So today, I'll be talking about topological phenomena in time-dependent systems. And specifically, I'll be talking about ways to probe them and to obtain quantized response functions. Okay? And I'm going to explain why you should think that's a problematic thing to achieve and how we get around the problems and actually kind of predict that you can observe quantized response functions. So let me just start kind of by an overview of the field. So, you know, you probably all heard of a lot of progress that's been done in the field of topological phase of matter, starting from the quantum Hall effect, and then the more recent discoveries of the quantum spin Hall effect, topological insulators, topological superconductors, and their application to topological quantum computing. And as some of you might know, these topological phase of matter have been classified. So starting with a classification, I'm not going to go into the details of these tables, but starting from a classification of non-interacting topological matter, phase of matter, topological phase of matter with symmetries, with interactions, the classification becomes very, very complicated. And I'm of course not going to go into these details. I'm going to ask a different question. What type of topological phenomena can we actually induce by basically driving a system externally with a time-dependent force? Okay, so if you want, this is some sort of modern alchemy. So you know that in the Middle Ages, the alchemists tried to convert lead into gold by shining moon rays, and we're going to see if we can kind of obtain new types of materials by shining maybe external laser fields or other types of driving forces. So this is my outline. I'm going to start by a brief introduction to basically the tools I'm going to use, which is Floquet theory. And then I'm going to describe a specific system, which is a two-dimensional topological phase of a periodically driven system. And I'm going to show you that in this type of system, we could obtain, in an analogy to the things we can observe in the quantum Hall effect, we can observe quantized two-terminal currents and quantized magnetization. And then I'm going to talk about the stability of these effects in the presence of interactions. So let me start with the introduction. So what I'm going to consider are Hamiltonians, quantum Hamiltonians, which are time periodic. So the Hamiltonian returns to itself after a period capital T. In this case, we could use Floquet's theorem, which basically tells us that we could decompose the evolution operator as a product of a periodic unitary, this is this W, times an exponential of a fixed matrix. Okay, so Floquet's theorem is basically what Bloch's theorem in time or the other way around. And the eigenvalues of this matrix, HF, we call quasi-energies. One thing to note about these quasi-energies, which is going to be important in the following, is that these quasi-energies are really defined only modulo omega, or 2 pi over t, because I could always move an omega from this part here to the periodic piece here. Okay? So these quasi-energies only live on kind of a circle, and they're defined modulo omega. Now, if we have a lattice system, then we need to think about Floquet-Bloch bands, which are basically characterized by their quasi-momentum, okay, as in any lattice system, and their quasi-energy. So this would be kind of a quasi-energy band structure for a Floquet system. Now, there have been several proposals in the literature to basically take a time-independent system, say a two-dimensional material like graphene, and basically subject it to, say, circularly polarized light and obtain a topological phase, or use resonant driving. I'm not going to go into these details, but I'm just going to say that there are methods to try to kind of induce topological phenomena, indeed by taking, say, two-dimensional, three-dimensional systems, or even one-dimensional systems, and driving them externally with say, an electromagnetic field. Some of these proposals have been realized in experiments. They're all optical experiments, so this is an all-optical system in which these ideas have been realized, cold atom systems, and even experiments in the solid state. So now I'm going to go into the question of how can we probe this type of phenomena. And what I want to remind you are these two kind of classic probes for the quantum Hall effect. One type of probe is just to try to measure, say, a two-terminal or conductance, or try to measure the Hall conductance of the system. And basically, what I would like to think, the way I would like to think about this probe is basically as an edge probe. So the current carried in this type of measurement is carried on the edge of the system. Another type of probe is to try to actually kind of do a bulk measurement. And one thing that was proposed by Streda was to try to measure the magnetization and take its derivative with respect to the Fermi energy. And indeed, this measurement too would give you a quantized value which is exactly equal to the Hall conductance. Okay, so both of these measurements measure the Hall conductance of the system, which is also its topological invariant, but they're kind of very different in the way they probe the system. So what I'd like to ask now is, can we actually use similar probes to probe these two-dimensional Floquet topological phases, or time-dependent topological phases? Can we have kind of a current measurement or a magnetization measurement? Now, one problem that you could imagine is the problem of heating. Okay, so in a system which is, in a quantum system which is closed, so it does not interact with an external heat bath, and at the same time is interacting with anybody's system, at long times, you can expect that the steady state of the system is kind of an infinite temperature state. What do I mean by that? I mean, this is a state in which all correlations look as if you'd have measured them in an infinite temperature state. There's no kind of any interesting correlation. The reason this happens, one way to understand it, is to think about what would particles do if I say start them in some arbitrary state. So let's start some particles here in this red band, and now I let the system evolve under this driving. Now, it's nice to describe what's happening in terms of collisions, but then if we do that, we realize that in the time-dependent system, in this periodically driven system, there is a type of collision that does not exist for a static system, and that's a collision which only conserves the energy mod omega. So in this collision, these two particles, say, collide, and you see that the one particle is actually transferred to this blue band, and if you check this process actually conserves the energy, or the quasi-energy mod omega. Okay? So this process is fine in the time-dependent system, but of course it would not be possible if this was a static system. And if you take into account these type of processes, after a very long time, you'd reach a situation where all the particles would kind of be distributed with an equal probability over all possible states, which is kind of corresponds to this infinite temperature state. Okay? So the question is, can we kind of avoid this, or if we, or the other possibility, if we try to kind of use any of these probes for these topological phases, we'd just see some very hot and not uninteresting state. Okay? And of course, what I would like to claim now that there's a way to get around this very hot infinite temperature fate, and there are actually several ways. One way you could think you could get around this infinite temperature fate is to actually couple to an external heat bath. Another possibility is to actually probe the system only on intermediate times and look at the kind of long-lived transients, and both of these approaches were explored in the literature, and I'm going to focus on a different approach in which you could use localization, disorder and localization, and basically drive the system into a situation where it's localized and cannot actually absorb heat, if you want, or absorb energy from the drive. Okay? And this is also, there have been kind of very recently many proposals for topological phases in these kind of localized systems, and I'm going to focus on a specific two-dimensional phase, which I'm now going to describe at some length. So this two-dimensional phase I'm going to talk about is this anomalous Floquet-Anderson insulator, and I'm going to explain what we mean by this title. Okay, so to understand this system, I first want to point out that the periodic-driven system actually allow us to have topological configurations which are actually not possible in static systems. And kind of one way to understand it is to think about the quasi-momentum and energy, which in a static system are kind of, you can depict them on this cylinder. For a Floquet system, as we said, the quasi-energy is actually periodic. It lives on a circle, and therefore the band structure of the system is actually placed on a torus. Okay, so this actually hints that there are more topological configurations possible in these periodically driven systems. So now, what I want to discuss now is the problem with having a chiral mode, a pure chiral mode in a static system, and I'm going to show you why this is possible in a time-dependent system. So let's, what I want to show you now is that if we cannot find a one-dimensional static system which only has a chiral moving band, so say a right moving band and no counter-propagating band. And the reason for this is very simple. If we now think about this system, saying we have some Fermi energy and we fill it up with electrons, if we now apply an electric field, the number of electrons would start to increase. The electrons would start increasing their momentum, and the number of particles will not be conserved. Okay, so this is something called the U1 anomaly in technical terms. But what it really tells us is we cannot find a system that only has this type of spectrum. Of course, we're used to hearing about chiral edge states in the quantum Hall effect, and the reason they are allowed is because they are actually connected to the bulk of the system. The bulk of the system, if we think about these these are chiral edge modes on the two sides of the system, so there's a mode going this way, another mode going this way. And they're, of course, connected through the bulk of the system here. Now, the bulk of the system can actually transport particles. It cannot be fully localized. We know it has a Hall connectivity or a Chern number. And once we apply our electric field, we're going to have the number of particles increasing on one edge and decreasing on the other. The reason this is allowed is because the particles are transferred through the bulk. Now, the reason I'm bringing this up is that the conclusion is that in the quantum Hall effect, if we have a non-zero Chern number, we also cannot have full localization of this band. Okay, so these things go hand in hand. Non-zero Chern number or non-zero Hall connectivity means that there could not be a complete localization of this band. Now, these considerations are different in a time-dependent or a periodically driven system. In a periodically driven system, we just conclude that the quasi-energy is periodic. Therefore, it's this corner of the quasi-energy and quasi-momentum diagram is actually the same as this corner here. So now if we apply an electric field, we could actually have the particle number be conserved, and there be no violations of particle number conservation. So the question is, can we actually find a system that only has a chiral band in a chiral quasi-energy band and nothing else? Now, if you work this out more carefully, as I'll now show you, this can actually kind of happen. It can happen as long as these edges are attached to a bulk which is fully localized. Okay, so I'm going to show you a system that has these chiral edge states, and at the same time, the bulk of the system is fully localized, so it cannot transport particles. And this is the big difference between the static and the time-dependent system. So indeed, this is this anomalous Floquet-Anderson insulator. And what it is it's a disordered system. Okay? that has fully localized bulk states, and at the same time, it has topologically protected edge modes. Now, what I would like to now explain is how to actually construct this type of system. Okay. So, to begin with, let's think about a clean system, no disorder. What I first want to claim is that we can actually have, in a time-dependent system, we can have topologically protected edge states coexisting with a trivial Chern number, so kind of topologically trivial bands in terms of Chern number in the bulk. And the reason is, this is of course not possible in a static system. We know that non-zero Chern numbers correspond to edge states, but in this time-dependent system, what we have to remember is that Chern number counts the number of edge states above your band minus the number of edge states below your band. And you can see that this diagram is totally consistent. So both bands have Chern number 0, and each band has one chiral edge state above it and one chiral edge state below it. So 1 minus 1 is 0, and this is perfectly fine. Of course, this would not be possible in a static system because this energy 0 and energy omega would not be identified. Now, you could ask, so if the Chern number is 0, what is the actual topological invariant that actually counts the number of edge states? And what we've shown is that there's a different topological invariant which actually knows about not only the momentum dependence of the evolution, but also on the full time dependence of the evolution. So it contains a derivative of the evolution operator with respect to time. Okay, so now what I would like to do next is actually construct a model, a very simple model that actually obtains this. There's actually various types of models. One type of model you could consider is actually take a two-dimensional system, a static system, and subject it to a weak homogeneous drive and see what type of kind of band folding you get when you do that. Another type of model would actually be to consider a model, a lattice model, in which all the hoppings are very strongly modulated in time. And this is the type of model I'm going to consider now. Okay? It's going to be a very simple model we could just work out on the fly. And it's going to give us exactly this situation I've described. Okay, so this model has a very simple structure. It's a square lattice, and it's a bipartite lattice. We have this black and the white sides. And we take our period of the drive, and we break it up into 4 steps. And in each step, we actually turn on only some of the links. So in the first step, we turn on only these red links here. In the second step, we turn on only the blue links, etc. And we do that by turning on the strength of the hopping in each sub-period such that exactly one particle is transferred from one side to the other. Okay, so there's let's start by fine-tuning the hopping to transfer exactly one particle between these two sides. Now, if we do that, you could actually follow the dynamics of a particle starting in any of these positions. And if you do that, you'd see that the particle would actually go around, say if I started here in the black side in the beginning of the period, the particle would actually hop around the plaquette and return it to its original position. Okay, so in that respect, the dynamics here deep in the bulk of the system is actually the identity matrix. Okay, after a full period, the particle returns to its original position and nothing happened. So this is, if I think about the bulk band structure of the system, it's actually a completely flat band. It's just the identity matrix. If I repeat this thing in the edge of the system, I see a different thing. At the edge of the system, if I start a particle, say, on this white side here, I would see that after this first part of the period, it arrives at this black side here, but from here, it has nowhere to go during the second part of the period. It has to stay there. And therefore, it actually only after a full period, it actually moves 2 steps to the left. Okay? This actually gives us a chiral edge state on this side of the system. This is this kind of green band over here, green chiral band over here. and another chiral edge state, which is this red band on this other side of the system. Okay, so so far what we've obtained, we've fine-tuned the decoupling, but what we've obtained is an exactly flat band and two perfect kind of chiral propagating modes on the edges of the system. This is the spectrum of the evolution operator after one period. Now we could also break up this flat band into more than one band by applying some sublattice potential. And I also want to remark that this type of dynamics, exactly this type of dynamics was actually obtained in an all-optical experiment, in actually two different all-optical experiments where they are actually seen both of the edge and the bulk dynamics in this type of system. So now we have this kind of fine-tuned model, but now let's deviate from it. And one type of deviation I can consider is just adding a disorder potential. I could also change the coupling. As I will show you, this is actually a phase, so I don't have to fine-tune anything. So I can now add a disorder potential, and I want to see what happens now. So the first thing to note is that I'm going to give you a claim, which we've checked numerically, and we can also kind of prove it by mapping to an Anderson model. Once you add disorder to this type of system, it actually localizes for an arbitrary amount of disorder. So any small amount of disorder you add to the system immediately fully localizes in the bulk. The localization length, of course, would be very large if disorder is very weak, but the system would be fully localized. And you could see this by plotting various quantities. One of them is this what's called level spacing ratio. The level spacing ratio is the parameter which tells you whether there is a level repulsion or not. In a localized system, we expect no level repulsion, while in a kind of ergodic system, we would expect more level repulsion, and this is why this parameter actually obtains these two universal values. So we have this universal value for in the delocalized regime and another value in the localized regime. Okay, so the claim from this, if you look at this plots carefully, is that the system becomes fully localized at all quasi-energies. However, if we look at the system with an edge, the system cannot be fully localized because of these edge states. These edge states are chiral, and chiral edge states actually cannot localize if I add disorder to the system. Okay? So now we obtain a very strange situation. If I look at this spectrum here, I obtain a very strange situation where I fully localize this bulk band. Okay, so these two bulk bands, this is just schematics, but this kind of bulk band has chart number 0. It immediately localizes, as I just said, and this band as well. But somehow, these edge states cannot be fully localized. Okay, so this is a strange situation because we cannot have an edge state terminating in a fully localized band. The reason is the following. The reason is if I take this system and now I kind of insert a flux quantum, say in the cylinder, okay, I need to have a spectral flow. So what I'm going to have that the edge states flow, they advance kind of by one unit of momentum every flux quantum. And that would mean somehow that this is a fully localized band and the state would terminate here, this would mean somehow that this flow is discontinuous. Somehow these edge states at the end of the, at the edge states where they actually meet the band have to terminate the flow, and this is not possible. One possible way to remedy this is to actually have an edge state appearing inside this localized bulk band as I add disorder. And this is indeed what happens. So as you add disorder to the system, the bulk band fully localizes, but you also have an edge state appearing where you previously had a bulk band, and now you have an edge state basically traversing the whole quasi-energy zone. Okay? You could see this in numerics where you check the dynamics at different quasi-energies, and you see that indeed you have a chiral edge state at every quasi-energy, but the bulk bands are, the bulk of the system is fully localized at every quasi-energy. One more thing I would like to note is that this is, I'd like to again emphasize that this is a phase. This is a phase which is different than a trivial Anderson insulator. And indeed, if you keep increasing the disorder strength, at some point you're going to have a transition into a kind of an ordinary Anderson insulator. Okay, so now I would like to, now I've described the system. Again, let me summarize this part. I've given you a model for a system which is at the same time has a fully localized bulk, and on the other hand, has basically chiral propagating edge states. So how can we now probe this system? So now let me consider these two types of probes. One type of probe is to consider a two-terminal measurement for the current, and then I'll talk about the magnetization. So to talk about the transport, let me just consider what indeed happens if we have this kind of chiral band and we completely fill it up with say, fermions. In this case, I can compute the average velocity of this band, and this average velocity is in fact quantized. It's quantized in units of the lattice spacing over the period. Okay? So the conclusion is if we manage to somehow fill up a chiral band, we'll be able to observe some sort of quantized currents. So how do we do this? By connecting a system, this type of system to leads. Okay? So the thing we came up with is to basically, kind of in contrast to what you do in a static system where you measure differential conductance, what we propose to do here is actually to take the system and actually connect it to leads and take a limit of a large bias between the leads. Okay? If you do that, you could imagine that particles from this kind of lead with positive bias would kind of enter the system and start filling up the edge states, maybe some region of the bulk as well, and this lead with the negative bias would actually remove them. So maybe in this sort of way, we'll actually be able to cover or fill up this edge state. And this is indeed what happens. One thing you could compute is you can compute the current as a function of the bias between the leads. And you see that as you increase the bias between the leads, you actually reach a quantized amount of current per period. So in the limit where the bias becomes larger than the period, but not much larger, so you see it's kind of here 2 in the units of omega, you basically start to see quantization. And I would like to emphasize this effect actually is, this order is crucial for this effect. If I would not have this order in the system, if I just had a clean system, I would not obtain any sort of quantization, as you can see from this blue curves. If you look at the particle distribution, once I connect these leads, in the steady state, you indeed see that what I just told you kind of holds. You manage to cover up completely some of these edge states, this portion of this edge state, and then the particles are transported through the edge state from one lead to the other. Okay? But if we look at this picture more carefully, we see that there is something weird going on. So this region of the system where the edge state actually lives is actually completely full. Okay? The particle density is just 1, and I'm considering the case where there's just one orbital per site. So in a region which is completely filled with fermions, there cannot be any currents. The system is just completely full, and it cannot carry any currents. Okay? Fermions cannot hop from one side to the other. So if you take this seriously, you realize that the current cannot be carried by this region, by the region where the edge state actually is. It necessarily is carried elsewhere, and the only other place it could be it's possible to think that it's carried is in the interface region between the field and the empty region. That's the region that can carry a current, and that's the region that actually carries the quantized current between these two leads. Okay, so this is now going to be important in what I'm going to discuss next. The current is actually carried in the interface between the field and the empty region. Okay, you could actually also see this exactly in this kind of toy model I've just presented, and you see that the currents cancel everywhere in the field region except at the interface. Okay, so now I would like to talk about this, the second probe, the magnetization probe. And I'm going to use what we just observed, the fact that the current is actually carried at the interface between the field and the empty region. So now I'd like to think about a different experiment. Before we looked at an experiment where I actually took a lead and two leads and I attached them to the system. Now I want to take the system, start with a region which is somehow initially filled with particles, with fermions. So this is this yellow region here. And then I want to let the system evolve, and I want to try to see what happens. I want to see if I could measure something quantized. And in fact, I want to measure a quantized magnetization in this setting. So if we look at the dynamics of the system, so since the system is localized, even if I evolve it for a very long time, particles can actually not fly away from this filled region. And as I just discussed, there should be a current carried in the interface between the filled and the empty region. And in fact, as we just saw, this current is going to be quantized. Okay? This current is going to be quantized, and now if we, what this basically tells us that there's basically a current loop flowing around this filled region here, and that kind of tells us that this region here carries some sort of magnetic moment, which is proportional to the current times the area. Okay? So now I'd like to, if I define a magnetization density using Ampere's law, so this is the kind of continuous law of Ampere's law, and this is its lattice versions, which if I kind of look at the current carried through this region, I can convince myself that there is a constant or kind of there is a quantized magnetization density deep inside this field region. Okay? Now the question is how to measure it. Okay? How would I measure? One possible way is to try to actually use a magnetometer. What I would like to also show is that we can actually use an interferometric probe to measure this magnetization. And this magnetization probe just uses the fact that the magnetization is actually the derivative of the energy with respect to the flux, okay, or to the magnetic field. Okay? In equilibrium, we're used to thinking about the magnetization as the derivative of the energy with respect to the magnetic field. And in this time-dependent system, a similar relation holds. The average magnetization over a period is the derivative of the quasi-energy with respect to a magnetic field. Okay? So in order to measure this quantized magnetization, what I need to do is actually I need to measure the energy shift as a result of adding a very weak magnetic field, a constant magnetic field, to these dynamics. Okay? So an interferometric probe can actually kind of use two, say, spin flavors for atoms, subject both of them to these dynamics, the time-dependent hoppings that I described, and to one of the spin flavors, apply a magnetic field, and then measure the phase difference. And if you measure the phase difference, you'd see that the phase advances in a rate which is exactly proportional to this quantized magnetization. So this would be a kind of a bulk probe. I'm now not invoking the edge of the system. The edge is at infinity, and I'm just probing the bulk of the system, and I'm basically reading out the topological invariant of the system directly from the bulk. So far, what I've talked about is I've talked about the system which is non-interacting. I only described kind of a non-interacting system. I've described kind of its dynamics in terms of single particle hoppings and disorder potential. But I've started the discussion by discussing whether we could actually observe topological phenomena in interacting time-dependent systems. So really, if I were to fulfill this promise, I need to somehow discuss what's the stability of all of these effects to interactions. Okay? So this is this last part of the talk. So what I would like to do now, I would like to kind of add interactions and discuss what can possibly happen. What I want to give you now is an argument that there should be a phase, okay, in parameter space, a well-defined phase, which is at the same time what's called many-body localized. Okay, so many-body localized for us would mean that the system does not kind of absorb energy indefinitely from the drive, and it does not reach its infinite temperature state, and actually it does remember its initial conditions. Okay. So there should be a phase which is many-body localized, and at the same time in this kind of anomalous topological phase. And the argument is very simple. So what we can consider is the dynamics I've just described with an add interactions, and just go to a rotating frame in which you cancel off all of the kind of clean part of the dynamics, the part with the kind of time-dependent hoppings. The nice thing about this transformation is that it's actually time periodic, because remember that the evolution operator for this kind of fine-tuned dynamics was actually identity after a full period. Okay? This means that this evolution operator is just time periodic. I mean, this kind of unitary operator is time periodic, and therefore we could actually go to a frame which is defined by this rotating wave transformation, and we could study the system in this frame. And what we end up is a system that has a time-dependent disorder interaction potential. However, if the frequency of the time dependence is high enough with respect to the disorder in the interaction, I can convince you that this system can end up in a many-body localized phase. The only caveat here is that there's still ongoing discussion whether MBL is indeed stable in 2 dimensions. But the bottom line is that this time-dependent system is as stable as a static MBL system in 2 dimensions. Okay? And I see that my time is running out, but we could also carry over the analysis of the magnetization to this time-dependent system, and we can indeed show that in this time-dependent system with interactions, you indeed should observe also a quantized magnetization if you're in this MBL phase. And we also have numerical evidence that supports this. There's a nice parameter here which tells us, this parameter alpha, which tells us we can actually squeeze all of the dynamics into a sub part of the period, and by this we actually enhance the localization of the system. So as you take this parameter to be smaller and smaller, the system becomes more and more localized, and delocalized only at a larger interaction strength. And indeed, also in these systems, we also have numerical evidence that indeed you see a quantized magnetization, although, of course, these are all finite size numerics, and we're not able to do any finite size scaling. One interesting question that I'd like to end with is kind of the fate of this system, whether in a situation where we also have edge state, can we actually have a many-body localized bulk coexisting with kind of thermal edge states, which are necessarily there at the edge of the system. Okay, so with this, I'd like to thank my collaborators and you for listening, and I'd like to put on this summary, and if there's any questions, I'd be happy to answer. Thank you.
Questions, please?
Right, so indeed, this is the point where MBL is very important, where many-body localization. So as long as we talk about single particle physics, there I think it's a well-defined issue. I mean, the disorder is also very important here. So once I add disorder to the system, I can ask whether I'm in kind of a trivial Anderson insulator or in this anomalous phase. I have this winding number, I have this kind of topological invariant, and it can obtain several values. So the claim is basically that any periodic driven system which is fully localized is in one of those phases that has one of the, some integer value for this winding number, for this topological invariant. The ordinary Anderson insulator, kind of the time-independent Anderson insulator, is one of these phases. It just has this winding number equal to 0. Okay? Now, it becomes slightly more complicated once you end interactions. You have to consider, okay, how do I define the phase now? So now I think you need to use basically MBL to have a properly defined phase. You need to say, okay, if I'm a system which is many-body localized, I could basically use this magnetization as a topological invariant. It's quantized. It cannot change unless I have some delocalizing transition, and I could use this to define my phase. Yeah. Right.
So, what allows these conditions to take place? They become delocalized?
Yeah. Yeah, it's a good question, and actually I don't have a full answer, and I'll explain why. It's actually quite complicated. So what you asked is exactly this plot, okay? So in this plot, we looked at the level spacing ratio. This is this parameter that tells us whether we localize or not. So it obtains this value of 0.6 for delocalized systems and say around 0.4 for localized systems. And we start at weak disorder, we're in this topological phase. And at some point, there is a phase transition. You see, we keep on increasing disorder. At some point, it seems like there's the delocalizing transition. There's a point where everything becomes delocalized, okay? And after this point, things become localized again. On this side of the transition, this is this winding number is equal to 1, so this is this anomalous topological phase, and here it's just a trivial Anderson insulator. You expect to, when you increase this order to be very, very large, you just have, all these dynamics don't matter. It's just localized. You could, however, the situation is more complicated. Let me just say this. What we looked at also is this level spacing ratio is a function of quasi-energy, and you can see it's completely flat. It looks like all states are delocalizing at once. Now, this actually might be an insufficient numerical precision in the sense that we cannot, if we went to larger systems, this plot might have more structure. There could be several different energies. We could have delocalized states and not delocalized states, and there's kind of an interesting dynamics. What you need to nucleate is nucleate states with Chern numbers, which then cancel the winding number. I could explain this in more detail. Yeah. Uh-huh. No, the other way around. I assume that both of them undergo this driving, both spins, but one of them I also add a very weak constant magnetic field. No, Zeeman orbital. So yeah, so it could be one flux quantum. Yeah. So suppose I add even one flux quantum on the whole system for spin, for one of the spins, right. And so what I want to measure is the difference in total quasi-energy between the downspins and the upspins. And the claim is, since there is a non-zero magnetization, there is a difference in the energy, which is basically, for weak field, which is basically this magnetization times the difference in the total flux, which is inside this field region. That's what I want to measure. That's the thing that advances in time.